How do we listen and speak at the same time over a communication channel? How does a telecom operator decide which duplexing method to use? Will the device that you use in China work in other parts of the world? Hi everyone, welcome back to the world of long-term evolution, 4th generation communication system. Today we will be discussing about duplexing.
Duplexing is the process of achieving two-way communication over a communication channel. It can be a half-duplex or a full duplex. Half-duplex. It stands for one-way communication at a time, which means the other party has to listen when you are talking, and you have to listen when other party is talking. So friends, do you have any device in your mind that uses half-duplex communication? How about a walkie-talkie device, having a push-to-talk feature? Now, let us look at second mode of communication, full duplex. It stands for simultaneous communication between two parties, which means both parties can interact freely. Now let us see how it is implemented in LTE, long-term evolution. Frequency division duplexing, FDD, is a method for establishing a full duplex communications link that uses two different radio carrier frequencies for transmitting uplink and receiving downlink. Both the channels are separated by a defined offset frequency, which is also known as guard band. The main purpose of selecting a guard band is to stop the interference between uplink channel and downlink channel. Now moving forward to TDD. Time division duplex is a technique by which the uplink and the downlink transmissions are carried over the same frequency by using synchronized time intervals. For example, a TDD communication path has been set up between Krishna and base station. Krishna can alternatively transmit and receive over time. Krishna using time slot 1 to transmit, slot 2 to receive, slot 3 to transmit and so on. Exact opposite with base station. As the transmission periods are relatively short, no time delay is noticed on voice transmissions. In between time slots, there are certain guard periods, so that signals traveling from base station can arrive at Krishna before the Krishna starts transmitting.
Let us see what are the factors that helps an operator to decide whether to use FDD or TDD before rolling out a full-fledged. Low latency. FDD offers very low latency, since transmit and receive functions operate simultaneously and continuously, whereas in TDD switch from transmit to receive incurs a delay that causes traditional TDD systems to have greater inherent latency. Equipment costs. No duplexer is needed to isolate the transmitter and receiver in TDD, whereas in FDD duplexer is needed. This is a key aspect, as cost of the user equipment is of major importance because of the vast numbers that are produced. TDD has the advantage here. Distance preferability. As the distance increases, the guard period also increases in TDD because the point-to-point signal propagation time increases. The increased guard period significantly affects the efficiency, whereas FDD does not have a problem with small or large distances. Unbalanced traffic. In real life, network volume consumed in downlink is much higher than in uplink. In TDD it is possible to dynamically adjust the capacity by utilizing more time slots for downlink than in uplink, whereas in FDD, the capacity is normally balanced in both direction. Spectral efficiency. TDD uses only one frequency, whereas FDD uses two different frequencies. So spectral efficiency in FDD is not as good as TDD. MAC layer complexity. MAC layer in TDD system is complex compared to FDD system, as it has to deal with accurate time synchronization between the systems, whereas in FDD there is no uplink and downlink switching mechanism at timescale.
Ultimately it depends on the network operator to choose as per requirement, convenience or feasibility. As far as LTE is concerned, it is defined to support both the paired spectrum for frequency division duplex and unpaired spectrum for time division duplex. There is same 3GPP specifications for both duplexing method, 3GPP 36.847. While the majority of the global LTE market is based on FDD technology, TDD is expected to see increased adoption in the US, China, Australia, Middle East, Northern and Eastern Europe, and Southwest Asia to gain a more pronounced position in the global LTE market. Keeping an eye on the future market, modern devices are being manufactured with support for both time division duplexing and frequency division duplexing.
So, next time when you buy smartphone, check which technique is used by your service provider and check the frequency bands supported by your smartphone. In the next video we will talk about shared medium technique, which is multiple access. So friends, don't forget to subscribe to our channel, like our videos and comments your views or suggestions. Thanks for watching. Has it ever struck your curious mind how 4G evolved from simple push-to-talk system? Is there any governing body which regulates the spectrum? What kind of services we will have in next generation of communication? So friends, let's start the journey of wireless communication. Mobile radio telephones were introduced for military communications in the early 20th century. Car-based telephones was first tested in St. Louis in 1946. This system used a single large transmitter on top of a high-rise building. A single channel was used for sending and receiving, similar to a half-duplex system. To talk, the user pushed a button that enabled transmission and disabled reception. Due to this, these became known as push-to-talk systems in the 1950s. To allow users to talk and listen at the same time, IMTS, Improved Mobile Telephone System, was introduced in the 1960s. It used two channels, one for sending and one for receiving, bringing telecommunication to full duplex mode.
In the 1970s, private companies have started developing their own system to evolve existing system further. Those private systems are Analog Mobile Phone System, used in America; Total Access Communication System and Nordic Mobile Telephone, used in parts of Europe; and Japanese Total Access Communication System, used in Japan and Hong Kong. Independently developed systems are called as first-generation communication. It was introduced in 1982 by Bell Labs and popularly known as Advanced Mobile Phone System, AMPS. The key idea here was to divide geographical areas into cells, and each cell was served by a base station so that frequency reuse can be implemented. As a result, AMPS could support 5 to 10 times more users than INTS. Major concern for the first generation was weak security on air interface, full analog mode of communication, and no roaming. Now, to implement roaming, individual organizations started working under one umbrella, European Telecommunications Standards Institute, ETSI, and developed second-generation system.
Second-generation cellular telecom networks were commercially launched in 1991 in Finland based on GSM standards. It could deliver data at the rate of up to 9.6 kbps. Three primary benefits of 2G networks over their predecessors were: phone conversations were digitally encrypted. It was significantly more efficient on the spectrum and allowing far greater mobile phone penetration level. 2G introduced data services for mobile, starting with SMS text message.
Further, to achieve higher data rates, GSM carriers started developing a service called General Packet Radio Service, GPRS. This system overlaid a packet switching network on the existing circuit-switched GSM network. GPRS could transmit data at up to 160 kbps. The phase after GPRS is called Enhanced Data Rates for GSM Evolution. It introduced 8 PSK modulation scheme and could deliver data rate up to 500 kbps using the same GPRS infrastructure.
During this time, the internet was becoming popular and data services were becoming more prevalent. Post 2.5G multimedia services and streaming started growing and phones now started supporting web browsing. Development of 3G. 3GPP-UMTS, the Universal Mobile Telecommunications System, succeeded EDGE in 1999. This system uses wideband CDMA to carry the radio transmissions, and often the system is referred by the name WCDMA.
Now, before we go further, let us understand how the governing bodies were developed. In the interests of producing truly global standards, the collaboration for both GSM and UMTS was expanded further from ETSI to encompass regional standards development organizations such as Arab TTC from Japan, TTA from Korea, ADAS from North America and CCSA from China. The successful creation of such a large and complex system specification required a well-structured organization. This gave birth to 3GPP, in which worked under the observation of ITUR.
ITUR is one of the sector of ITU. Its role is to manage the international radio frequency spectrum and to ensure the effective use of spectrum. ITUR defines technology families and associates specific parts of the spectrum with these families. ITUR also proposed requirement for radio technology. 3 organizations started developing standards to meet the requirements proposed by ITUR. 3GPP, 3GPP2, IEEE. Evolution of 3GPP started from GSM to long-term evolution advanced. Evolution of 3GPP2 started from IS-95 to CDMA revision B. Evolution of IEEE started from 802.16 fixed WiMAX to 802.16m. Since 3GPP was dominated and widely accepted, we have only incorporated roadmap evolved by 3GPP. Now coming back to third generation.
The goal of UMTS or 3G wireless systems was to provide a minimum data rate of 2 megabits per second for stationary or walking users, and 384 kilobits per second in a moving vehicle. 3GPP designated it as Release 99. The upgrades and additional facilities were introduced at successive releases of the 3GPP standard. Release 4. This release of the 3GPP standard provided for the efficient use of IP. This was a key enabler for 3G HSDPA. Release 5. This release included the core of HSDPA. It provided reduced delays for downlink packet and provided a data rate of 14 Mbps. Release 6. This included the core of HSUPA. With a reduction in uplink delay, it enhanced uplink data rate of 5.74 Mbps. This release also included MBMS for broadcasting services. Release 7. This release of the 3GPP standard included downlink MIMO operation as well as support for higher order modulation of up to 64 com. Either MIMO or 64 com could be used at a time. Evolved HSPA Plus provides data rates up to 28 megabits per second in the downlink, and 11 megabits per second in the uplink.
This brings us to the most awaited part, 4th generation system, long-term evolution. Initial goal of telecommunication was mobility and global connectivity, but as the technology evolved, the services started expanding. Now services were not restricted to voice and SMS only. For this expansion and efficient execution in long-term evolution, whole new architecture was adopted for both non-radio part, which is SAE, System Architecture Evolution, and radio part, using pure IP architecture, packet switching. To fulfill the requirement proposed by ITUR, study group formed, and LTE standardization began in 2004. Large number of telecom companies collaborated to achieve their common vision. In June 2005, Release 8 was finally crystallized after a series of refining. Some of the significant features of Release 8 were reduced delays for both connection establishment and transmission latency, increased user data throughput, increased cell edge bitrate, reduced cost per bit, implying improved spectral efficiency, simplified network architecture, seamless mobility, including between different radio access technologies, reasonable power consumption for the mobile devices. These requirements were fulfilled by advancement in the underlying mobile radio technology. The 3 fundamental technologies that have shaped the 4th generation system in the radio interface were multi-carrier technology, multiple antenna technology, and the application of packet switching to the radio interface. As a result of intense activity by a larger number of organizations, the specifications for the Release 8 was completed by December 2007. The first commercial deployment took place by the end of 2009 in Northern Europe. In the subsequent releases, multiple services such as multi-cell HSDPA, HETNet, coordinate multipoint, carrier aggregation, Massive MIMO and many more were targeted for a rich customer experience.
Now it's time to move from services to multi-services approach. In other words, from LTE advanced to next generation communication system, which is 5th generation. Features have been planned to be added in the 5th generation or next generation system are pervasive networks, where a user can concurrently be connected to several wireless access technologies and seamlessly move between them. Group cooperative relay. This is a technique that is being considered to make the high data rates available over a wider area of the cell. Cognitive radio technology. It would enable the user equipment to look at the radio landscape in which it is located and choose the optimum radio access network, modulation scheme and other parameters to configure itself to gain the best connection and optimum performance. Smart antennas. Another major element of any 5G cellular system will be that of smart antennas. Using these, it will be possible to alter the beam direction to enable more direct communications and limit interference, also increase overall cell capacity.
So friends, here we have covered history of wireless communication, starting from single-channel based push-to-talk system to multiple services based purely advanced digital communication system. In the future videos we will start exploring fundamental of advanced communication, which will help us to understand next generation system better. Don't forget to subscribe to our channel, like our videos and comment your views or suggestions. Thanks for watching. A wise man once said that necessity is the mother of invention. We have shown how in the beginning cavemen could communicate verbally, but when the need for long-distance communication arose, several techniques such as smoke signal, pigeons, Pony Express, semaphore flag, etc. were developed. But they were not enough. The desire for fast and reliable communication gave birth to wireless communication using radio waves. It wasn't easy in the beginning for ITUR. Unlike wired communication, it was very difficult to establish a full-fledged communication system and govern them. In first generation, the goal was to provide a rich wireless experience. But it was not matured enough to provide a smooth service. As the technology grew, the organizations from different countries came together to achieve global connectivity, and second-generation wireless communication was developed. The need for higher data rate resulted in evolution to third generation and fourth generation, as this channel is purely dedicated to advanced communication, which is fourth generation. Here we will broadly cover the underlying technologies, which are used in air interfaces like OFDMA, SCFDMA, TDD, FDD. We will also discuss how spectrums are allocated to telecom operators and how operators distribute the bandwidth among the users. We will show you how frames are structured and how throughput is calculated in different radio conditions. Once we have a brief idea about the underlying technologies, we will dive deep into LTE architecture, where we will discuss the different nodes and the different protocols that are used in LTE. We will also discuss different LTE states and identifiers. In the later part, we will discuss LTE procedures such as the attach, detach, cell reselection and handover, where we will discuss authentication, NAS and RC security, policy and charging, service data flow and bearer level QoS. So friends, fasten your belts for a ride through the world of long-term evolution. Don't forget to subscribe to our channel. Happy learning! All of us get excited when we see the symbol. But how does it work? Ever wondered how millions of subscribers are served by telecom operators simultaneously? Hi everyone! Welcome to the world of long-term evolution. Today we will show how multiple users access network using multiplexing.
In the last video we have shown how two signals were combined over a common pathway in duplexing. So, what exactly is multiplexing? Multiplexing is the process of combining multiple signals and transmitting them over a common channel. Then what is multiple access? When multiplexing is used to allow multiple users to communicate over a single common channel, we call it multiple access. In other words, Multiple access is nothing but the application of multiplexing. So here's a Wi-Fi hotspot sharing its internet connection among multiple users by providing them a frequency block over which they can transmit and receive data. The greater the size of this block, greater is the throughput. Telecommunication systems, which mostly use radio waves as a communication link with end users, have employed several ways to share this resource.
FDMA, which uses frequency division multiplexing, provides chunks of the frequency spectrum to each user for data transmission. Generally, the data is generated at baseband and modulated at varying radio frequencies. Guard bands are introduced to avoid any interference. AMPS or the first generation analog systems used FDMA to provide each user a duplex channel with one-way bandwidth of 30 kHz. TDMA, which uses time division multiplexing, allows multiple users to share a common frequency band by allocating different time slots. Thus, in an N-channel TDMA, where each channel is given a time slot of T seconds, signals coming from each user will be transmitted at intervals of N into T seconds. This technology was used in the 2G systems like GSM, GPRS and EDGE. Each user was provided one of 8 TDMA slots and a bandwidth of 200 kHz. Dynamic resource allocation meant more users could be supported, but each channel could support only 8 active users at a time. CDMA, based on code division multiplexing, is a technique in which the data bits are modulated by a high-frequency orthogonal sequence of bits such as Walsh codes or pseudo-random codes such as gold codes to spread the signals over a large frequency band. Multiple such signals from different users are then transmitted over the same frequency band. In order to retrieve the signal, receiver must have the same spreading sequence, which is multiplied to this composite signal in a process called dispreading. This makes CDMA very secure and robust. It was used in 3GPP2 standards such as CDMA and CDMA Evolution Data Optimized standards. Wideband CDMA or WCDMA spreads the signals over an even higher bandwidth. This was used in the 3G standards of 3GPP from UMTS to HSPA+, where the available bandwidth was 5 MHz compared to 1.25 MHz used in CDMA. There are other multiple access techniques like wavelength division multiple access, which is used in fiber optics, and space division multiple access, which refers to spectrum reuse over non-overlapping areas.
As the number of users and their demand started growing, communication networks evolved from 1G to 4G. Radio part was significantly enhanced from GSM to HSPA+. Now, focus was shifted towards better spectral efficiency by using higher modulation order like QPSK, 8PSK, 16Com, 64Com, etc. WCDMA improved upon some of the problems of earlier generations like, first, low data rates. In GSM, effective bandwidth for a user was only 25 kHz. Second, congestion at peak hours, as the frequency chunks and time slots were very limited. Third, resource wastage. Resources remained idle when users were inactive. Fourth, poor spectral efficiency, due to guard bands and guard periods used for avoid interference. But, exhaustion of spectrum, need for even higher data rates, and spectral efficiency lead us towards OFDMA. OFDMA comes with several advantages over WCDMA like bandwidth scalability, carrier aggregation, low intersymbol interference. OFDMA uses orthogonal subcarriers equally spaced at 15 kHz. Users are provided a subset of these subcarriers for data transmission. Unlike FDMA or TDMA, OFDMA allows the users to access variable bandwidth depending upon the resource availability. Also, since these subcarriers are orthogonal, there are no guard bands between them. It was first introduced in Wi-Fi, and subsequently in WiMAX, by IEEE, but as WiMAX lacked backward compatibility and support for mobile wireless at its inception, operators remained stuck with WCDMA. This changed with the introduction of LTE, which brought OFDMA to the forefront of today's mobile networks.
So, Today we showed what were the different multiple access techniques that were used in various generations of wireless communication. In our next video, we will dive deep into OFDMA and SCFDMA, the two pillars of 4G. Hope you enjoyed the video. Don't forget to subscribe to our channel to stay updated. Happy learning! Hello friends, today, how can we stream a full HD movie seamlessly? Which seemed impossible in legacy networks. So friends, in this video we have shown what are the limitations of wireless channel, how wideband single channel are inefficient for transmission. To overcome, how wideband single channel is divided into small subcarriers and increase efficiency by reducing delay spread. How concept of orthogonality is introduced in FDMA and achieved multifold throughput. Hi everyone, welcome back to the world of 4G.
Previously we have shown how mobility and global connectivity was achieved by introduction of wireless communication. But there are several complexities associated with wireless channels. Multipath fading. Unlike a wired channel, which uses a fixed path, the signals in a wireless channel can reach a user using multiple paths. All these signals known as multipath components may have different channel gain and time delay. This combined effect causes what we know as multipath fading. Delay spread. As a consequence of multipath propagation, the duration of a symbol gets extended. This may interfere with the next symbol. This is called inter-symbol interference or crosstalk. Guard periods are introduced to avoid crosstalk. Frequency selective fading. Signals having bandwidth higher than the coherence bandwidth of the channel faces variable attenuation at different frequencies. This ultimately distorts the signal, and giving rise to frequency selective fading. Complex channel equalization techniques are employed to reduce it. Inter-channel interference. Often signal bandwidth of adjacent carrier frequencies overlap with each other, giving rise to inter-channel interference. Guard bands were introduced to avoid inter-channel interference. All these limitations, compounded with the scarcity of bandwidth, gave rise to multiple access technique, OFDMA. Before diving into OFDMA, let us understand multi-carrier wireless transmission system.
Suppose a signal is to be transmitted over a bandwidth B, and carrier frequency FC. Then symbol time for this would be TS equal to 1 by B. For a single carrier wideband channel of let's say 1 MHz, the symbol time will be 1 microsecond. Given that the delay spread of the channel is of 2 microseconds, the combined symbol time would be 3 microseconds. Which means delay spread occupies 66% of the combined symbol time, thus reducing the efficiency of the channel by 1/3. As delay spread is difficult to control, the effect of delay spread can be minimized by using multiple subcarriers of lesser bandwidth. So instead of having a single carrier of 1 MHz, we divide it into 100 subcarriers of 10 kHz. Each having a symbol duration of 100 microseconds. So a delay spread of 2 microseconds will have a negligible effect over the channel efficiency. This concept is used in FDMA, which uses slowly modulating subcarriers of higher symbol duration. As these subcarriers are modulated with data, they gain bandwidth centered around the subcarrier's frequencies. Guard bands are used to separate them in frequency domain. We can represent this transmitted signal in the equation form as shown here, where summation of individual symbol multiplied with different carrier frequencies and transmitted at radio frequencies. OFDMA or orthogonal frequency division multiple access is a special case of FDMA, where users are provided a set of subcarriers overlapping in frequency domain. However, these subcarriers are specially designed to be orthogonal to each other, which allows them to occupy the same bandwidth without any interference. This in turn negates the use of guard bands. As a result, the subcarriers can be closely packed to increase channel efficiency. Now, before looking at the multiple access part, Let's understand how OFDM or orthogonal frequency division multiplexing works, and how it's used in long-term evolution.
In OFDM, high-speed data streams of large bandwidth are split into parallel, slower substreams of lower bandwidth called subcarriers. These subcarriers are centered around frequencies in multiples of 15 kHz on both sides of DC. As the lowest subcarrier is of 15 kHz, symbol duration, TS, is equal to 1 by 15 kHz or 66.7 microseconds. Consequently, a one subcarrier can provide a symbol rate of 15 kilosymbol per second, which is analogous to having a symbol rate of 1 symbol per second for 1 Hz of bandwidth or half the Nyquist rate. Unlike in GSM or UMTS, LTE supports variable bandwidth as shown in the table. As the bandwidth increases, so does the number of subcarriers in it. Let's take, for example, LTE bandwidth of 20 MHz, which has 1,200 subcarriers and thus a subcarrier bandwidth of 18 MHz. 2 MHz used as guard band. Here we have 600 subcarriers on both sides of the DC frequency. All these carrier frequencies are harmonics of 15 kHz, varying from -9 MHz to 9 MHz. In time domain, these subcarriers will be represented as everlasting sinusoids at these carrier frequencies as shown. However, in order to transmit data over these subcarriers, they are loaded with modulation symbols that represent the constellation points of digital modulation schemes, like UPSK and nth order comms. Also, the symbol duration for each of these subcarriers is always equal to 66.7 microseconds, which means that all these subcarriers have a whole number of cycles in one symbol duration. As we know that a rectangular function can be represented in frequency domain as a sinc function which is centered around DC. When multiplying a signal to a carrier frequency in time domain, signal will be shifts in frequency domain by the same amount of carrier frequency.
Thus we can represent these modulated subcarriers in frequency domain as a series of sync waves centered around the carrier frequencies. Basically, we are having 1,200 such sync waves. There are 2 points to be noted here. Firstly, the subcarriers are overlapping in frequency domain. As we can see, the subcarriers are placed in a manner that all the other subcarriers have a zero component at the peak of one subcarrier. Such subcarriers are called orthogonal. As a result, a mobile can sample the frequency and phase, without any interference from neighboring subcarriers. Orthogonality is achieved by ensuring that all the subcarriers have same symbol duration TS, and the subcarrier spacing is maintained at delta F equal to 1 by TS. Secondly, presence of negative frequencies. It can be explained by the fact that the subcarriers are transmitted below the radio carrier. So friends, today we learned how information is split into smaller subcarriers in multi-carrier modulation, and how efficiency was increased by placing them orthogonally. In our next video we will show how data starts its journey as a stream of bits and are finally transmitted as radio signal. So friends, don't forget to subscribe to our channel, like our videos and comments your views or suggestions. Happy learning! Streams of data, in the form of bits, reaches network gateway from various sources. The gateway forwards it to the E node B, but how does the E node B converts them into radio signals and transmit them to the user over the air interface? How does the user equipment communicate back with the node B? Hello friends. Welcome back to the world of 4G. Today we will discuss uplink and downlink data transmission in the network.
As discussed earlier, data is transmitted in OFDMA over parallel subcarriers of 15 kHz. The subcarriers are further divided on the time axis as blocks of one symbol duration, or 66.7 microseconds. This basic unit is known as resource element. Each resource element carries one symbol. Now, in order to transmit data over these resource elements, First, data is modulated with specific modulation scheme. This scheme depends on the physical channels mapped on the resource grid. Suppose we have 8 bits of data to be transmitted using QPSK modulation. The data will be divided into 4 parallel streams of 2 bits. Phase and amplitude assignment is done according to the QPSK constellation. Finally, data is placed over the resource elements by adjusting the phase and amplitude of subcarrier to those derived for the data stream. Mathematically, it means multiplying the complex modulation symbol to the corresponding subcarrier frequency. Thus, in a 20 MHz channel, all the 1200 resource elements carrying 1200 symbols over 1200 subcarriers are modulated with appropriate modulation scheme. Now, since the data is modulated over 1200 subcarriers, a transmitter will require 1200 oscillators for its generation, and another 1200 will be required by the receiver for proper demodulation. The hardware complexity and sheer amount of power consumption would have left OFDM to theoretical idea and far from implementation. OFDM was made reality with the advent of digital signal processing techniques. So, instead of using 1200 oscillators, IFFT solves this problem by converting the parallel frequency domain signals into samples of a composite time domain signal, which are much easier to generate at transmitter side. All we need to do is to send these time domain samples at radio frequencies. As the data is being sampled by IFFT, samples must be taken above the Nyquist rate for faithful reproduction at the receiver. For an LTE spectrum of 20 MHz, the highest frequency component is 9 MHz, which means the sampling rate should be greater than 18 megasamples per second. In other words, 1200 samples per OFDM symbol of 66.7 microseconds. Since UMTS had a sampling rate of 3.84 megasamples per second. To achieve backwards compatibility, sampling rate in LTE is taken as multiple of 3.84 megasamples per second. Thus for 20 MHz spectrum, which has a sampling rate of 30.72 megasamples per second, there are 2048 samples per symbol in OFDMA. The FFT size of the IFFT processor thus depends on the LTE bandwidth as shown.
Now, previously we have shown, in wireless channel due to multipath propagation, we face delay spread and inter-symbol interference. We have also discussed how its effect can be reduced by increasing the symbol duration. Also, how guard period were used to eliminate it. But abrupt changes in time domain during transition period, from symbol to guard period, causes intercarrier interference in frequency domain, and disturbs the orthogonality between subcarriers. So in OFDMA, we employ a more complex kind of guard period, called cyclic prefix, in which end part of a symbol is transmitted in the preceding guard period. It also ensures orthogonality between the subcarriers, by keeping the OFDM symbol periodic over the extended symbol duration and therefore, avoiding intercarrier and interchannel interference simultaneously. Since OFDMA uses composite IFFT samples, cyclic prefix is added by taking some samples from the end of a symbol period, and placing them at the beginning.
Now this time sampled signal is converted into analog wave by a digital to analog converter. Further, composite waveform is modulated at the desired radio frequency for transmission. For an example, an operator having license for 2320 MHz to 2340 MHz. The 18 MHz band will be mapped from 2321 MHz to 2339 MHz using analog modulation. And finally, the A node B transmits signal over air. In node B, informs the user about the allocated subcarriers and the corresponding modulation scheme. So, when the RF signal reaches at the user's terminal, all these processes are reversed and finally user is able to receive the data intended for it.
Although there are many positives in OFDMA, but IFFT summation of multiple parallel subcarrier results in high peak to average power ratio. High PAPR results in high power consumption for signal generation. But handheld devices have limited power capacity. This makes OFDMA unfavorable for uplink transmission. In order to overcome this, LTE uses SCFDMA in uplink direction. In OFDMA, we have one-to-one mapping between symbol and subcarrier, but SCFDMA allows a symbol to be transmitted in parts over multiple subcarriers. For example, in OFDMA one symbol occupies one subcarrier of 15 kHz, but in SCFDMA, same symbol is distributed among multiple subcarriers of 15 kHz. In short, SCFDMA behaves like a single carrier system with short symbol duration compared to OFDMA. To achieve this, SCFDMA introduces the endpoint FFT block right after the serial to parallel converter in the OFDMA structure. The FFT block converts parallel sequence of symbols in time domain to different frequency points. Now, peak to average power ratio is proportional to the square of number of carriers involved. SCFDMA reduces PAPR by reducing the number of carriers. Obviously, there are problems in single carrier transmission as we discussed earlier, but the side effects are reduced by ensuring that the total bandwidth over which a symbol is transmitted is still not too high. Apart from this, remaining block in the uplink direction is same as used in downlink direction.
In our next video, we will be talking about physical, transport and logical channels used in long-term evolution. So friends, don't forget to subscribe to our channel, like our videos and comments, reviews or suggestions.
Previously we have seen how data is transmitted over the air, but these data are transmitted in multiple streams for better efficiency. But how are these signals classified? Who maps them to the corresponding channel? Hello everyone, welcome back to Fundamentals of 4G. Today we will discuss logical and transport channels.
The work of telecom operator is to deliver information to end users faithfully, using complex techniques. These information are transferred through various paths known as channels. To understand this complex concept, let us take a simple real-life example. Consider a case of a big logistics company, such as India Post. Every day thousands of different kinds of mails, or goods, such as normal post, speed post, books, mobiles, soft toys, clothes, jewelries, shoes, TV, refrigerators, cars etc. comes to its office for delivery. And for secure and efficient delivery of the mentioned items, the company will use different modes of transport systems. The mode of transportation may vary, from two-wheelers, four-wheelers, 16-wheeler vehicles etc. Now, it is almost impossible for a single team to handle the overall process and effectively route all these products to its destination. So, the company executes this process simply by splitting the work among multiple teams. First team, let's say Team X, has clear information about the products. It categorizes them logically such as lightweight, heavyweight, heavy automobiles, books, clothing, etc. Team X then hand it over to Team Y. Now, based on the segmentation logic passed by Team X, Team Y decides the mode of transportation to be used. For example, two-wheelers will carry lightweight goods. Trucks will carry heavyweight goods. 16-wheeler container will carry heavy automobiles. Rest categories can be mapped in a dedicated transport group.
In addition to that, Team Y also has to decide, 1. If delivery failed to reach destination, Team Y can either cancel the delivery or go for different mode of transportation. 2. If there are multiple product categories in a single transport system like dedicated transport group, team can set priority as per requirement or situation. So Team X and Team Y takes the decisions, but the vehicle arrangement and the physical transportation is executed by Team Z. Here, Team Z is working at the front end, and is actually transferring the items. Now, let's say an TV needs to be delivered. So Team X and Team Y have categorized it as heavyweight, which needs to be transported in truck. Now the same vehicle is carrying other items such as refrigerators, microwave, other TVs, etc. So at offloading point the person has to go through all the packages to extract the exact TV and hand it over. So, for convenience, Team Z will arranges the packages in a defined way, and also keeps a record of arrangements, so during offloading they can efficiently extract the item and deliver it. From this example we can say, Team X decides what is to be transported. Team Y decides how it is going to be transported. And Team Z acts on where exactly it has to be transported.
Now, let us understand how similar concept is implemented in telecom network. As we said earlier, telecom operator has to deliver data to the users using complex techniques. These data can be classified on application layer as user plane data, which is actual data intended for user. Control plane data, the data which are necessary for successful delivery of user plane data. These control plane and user plane data are further classified for efficient delivery, which is similar to the role of Team X in real-life example. Here in LTE protocol stack, radio link control layer performs this logical categorization, and the process is known as RLC segmentation or concatenation.
So, there are 5 logical channels for control plane traffic. Paging control channel. This channel carries paging messages, which the E-node B transmits if it wishes to contact mobiles that are in idle state. Broadcast control channel is the most vital channel. It is used for broadcasting system control information to the mobile terminals in the cell, including downlink system bandwidth, antenna configuration, reference signal power, etc. Common control channel, when device switched on, and device is attempting to latch to the network, it doesn't have any radio connection established. So the device uses this channel for exchanging control information. Dedicated control channel. Once dedicated radio bearer resource has been set up at both device and E-node B end, dedicated control channel is used to transfer control info. Multicast control channel. This channel is used to carry control informations of a group of users in a cell for multicast broadcast services. There are 2 logical channels for user plane traffic. Dedicated traffic channel. This channel is used for both uplink and downlink of user plane data between user and network. Multicast traffic channel. This is a unidirectional channel. It is used to transmit traffic data from the network to multiple of users for multicast broadcast services, such as real-time broadcasting of sports, events, etc. These all channels are like Team X in our example, who decide or segregate the traffic on the basis of type of data.
After segregation, we need to think of transportation for every logical channel. This is similar to assigning of transport vehicle in our example, which was performed by Team Y. Here this task is performed by MAC layer. In downlink, 4 type of transport channels are used, from which the paging, broadcast channel are mapped one-to-one from respected logical channels, and remaining downlink shared channel are mapped from multiple logical channels. Now, we said earlier that broadcast channel is used to broadcast system information, and this contains large number of signaling data. So, the system information is split into 2 parts. MIB, master information block, since it carries a system critical information to acquire the cell, and it passes through broadcast channel. SIB, system information block. It contains other dynamic system information to access the cell, so it passes through downlink shared channel. In order to maintain healthy radio connection between user and network, user should have dynamic information of that cell, and for that user has to decode SIB from downlink shared channel. which transmitted to resource element on physical resource block. But user is unaware of this physical resource block, so user has to decode MIB first, which gives system critical information along with scheduling information for SIB. Then SIB can be decoded.
The transport channels used in uplink are similar to downlink. The logical channels such as common control, dedicated control and dedicated traffic channels are mapped into the uplink shared channel. As there are no paging, broadcasting and multicasting messages in uplink direction, so this channel is not present in uplink direction. However, there is one more channel in transport that has no corresponding logical channel in uplink direction. That is random access channel. At the initial stages, the user is not synchronized in the uplink, and user cannot send any data without getting synchronized in uplink direction. So random access process is initiated for uplink synchronization. What we have seen so far is, in LTE protocol stack, the logical layer, known as radio link control, segregates the data from upper layer into different groups. Then the transport layer, known as medium access control layer, maps them to physical layer through transport channels. But mapping multiple logical channels in a transport channel, or simple words multiplexing the logical channel, is not the only job of MAC layer. As per 3GPP 36.321, the functions of MAC layer are 1. Multiplexing, demultiplexing of logical channels, which is already discussed. 2. Logical channel prioritization. We have shown in the example earlier that sometimes many dissimilar items were grouped in the dedicated transport group. Similarly, in shared transport channel, for uplink and downlink, multiple logical channels are mapped. It is the work of MAC layer to prioritize these channels and assign them resources accordingly. 3. Hybrid ARQ retransmission, which stands for Hybrid Automatic Repeat Request. If somehow the receiver's MAC layer could not decode the data or the decoded data was found to be corrupted, then the receiver's MAC layer will send negative acknowledgement, based on that the transmitter's MAC layer will have to retransmit. 4. Random access control. As told earlier, the random access channel is the only transport layer channel that doesn't have any logical channel. Batch process is solely taken care by MAC layer.
So friends, we have seen how data are sorted and mapped into various transport channels. In our next video we will discuss the function of MAC control and the brain behind all these operation, which is MAC scheduler module. We will also discuss the functioning of TMZ, or the physical channels which actually transports the data. You can comment your doubts or suggestions and subscribe to our channel to stay updated. Happy learning!